So there's various pieces of profit that we can look at. I just wanted to throw this out as a line of thinking here. As fixed costs or as levels of an input such as nitrogen fertilizer go up, you can see there's a response curve, the curve here, that levels off when we get up to about our optimum economic yield. The maximum yield is a little higher than that, but it's usually not economical to go quite that far. We back off a little bit to get our maximum economic yield. Same time, our costs go up pretty much in proportion to the fixed costs, or to your variable costs. Your fixed costs are going to be the same all the way across there. So as we put on more inputs, we get a straight line increase. So if we're down here on the lower part of the response curve, and we put an increment of input in, we see on the left side the percent of maximum yield. We see the increment of increase in the percent of maximum profit that we have. But if we move out further on the response curve, if we're up here where we're not getting too much response to the next increment of input, then the change in profit or change in yield that we get isn't quite as great. Now, that doesn't mean obviously this is our most economical point, so that's still we'd want to work to that point. But the point of this is that if we get into an economic situation where we can't afford to increase our inputs for a year, that we need to back off and drop down a little bit on that input, say cut your nitrogen rates or phosphorus rates, the impact isn't very great if we're managing up here at this higher level. In other words, we're at a high soil test level, and we're not as dependent on this year's fertilizer application to give us our increase in yield. So we could drop back and we'd only lose this much. But if we're down on this part of the curve, we really can't afford to drop back on inputs because we'd lose a considerable amount of profit if we did so. So my idea here is that as we manage at a higher level of management for all inputs, we have a lot more flexibility of being able to drop one of those out for a year and still maintain our profit and yield levels. Hope that's not too confusing. Moving into site-specific management, then, this is where we start looking at all the components and the pieces. We have to think in terms of layers. We have our soil map. We have a soil test phosphorus map, a soil test potassium map, maybe a map of last year's yields. And maybe we have several years of each of these. We could have any number of maps that we can draw information from. And the longer we work with precision farming and collect these data, the more information we have, more seasons of crop we have to draw from to fine-tune our decisions. And then we have satellite controls with GPS. We can monitor where everything is done, and that allows us to make changes with respect to the information that's on these layers. So it could be planting rate, fertilizer, chemicals applied, or your broadcast fertilizer application. It could be scouting information when you go to the field. I encourage you to take a handheld computer or a notebook, whatever you want to use, and a camera, and record what you're seeing out there, and record it with the GPS coordinates. Most of our cell phones and cameras even now have built-in GPS so that you can record where that picture was taken or where those notes were taken. It becomes very valuable as we move into the later in the season and something goes wrong with the crop. You can go back and check those notes and say, did I observe anything in this area that might give me a clue to what the cause is, and maybe help you to correct it for next year. Of course, ultimately, at the end of the year, we have our yield map, and the yield map integrates everything that's happened to that crop. The crop has its maximum potential yield is when the seed's in the bag. As soon as you open the bag and put the seed in the ground, everything that happens to it from that point on it nurtures and feeds the crop, but it also, a lot of things go wrong, and the potential yield declines for every negative that comes into play. Kind of a bad or a negative way to look at it, but the point is we want to make sure that we eliminate those negative influences and profit-robbing factors that come into play. So these are all some of the tools for best management practices. Precision guidance is probably one of the hottest ideas going on today, and this picture I think shows, you can see how perfectly straight those rows are as we go across the field. Now this is really neat, and then they zero in and look at it. It doesn't GPS guidance, it's a good driver on a team of horses. So maybe all this precision farming isn't so new after all. The point is we're always building on the past. We're trying to do better than we can. You don't have to have the precision tools to make all these things happen, but they sure do help. We consider the whole system. We need to systematically include all those components to define the best management system for a field. The power of precision technology really lies in GIS. And then determining the interaction among the layers is one of the things that GIS analysis can do. It can tell us the impact that phosphorus level has on yield, for example. And that's very important as we move forward. It works with on-farm research results as well as with university and industry research results. It helps us to make better informed, site-specific decisions that are targeted directly for the field that we're working with. The number one challenge for precision ag, I see, is the agronomic relationships among all of those crops, the soils, the practices that come into play, and how we can refine those relationships so that we can take advantage of the hardware and software tools that are available to us. So management is really putting all those pieces together in a decision process. And I think right now we're suffering from a technology agronomy gap. There are many changes in direction of agronomic research. We've had a lot less applied field research going on in recent years, and we're falling behind in being able to really answer some of those questions. We've focused a lot more on the high-tech genetic engineering and some of those things, but we really need to go back and continue looking at what is the right nitrogen rate for this new genetic variety, and what is the right phosphorus level, and how deep are the roots going, how deep do we need to place the fertilizer for that, and those kinds of decisions. We've had a big reduction in funding for applied agronomy. There's really just not much money in that. We've, as a result, have reduced our staff at universities and in agribusiness to do that type of research. I think it's a challenge that we need to worry about. Another result is that we have fewer graduate students being supported. That means fewer new scientists being generated to carry on this kind of work in the future. And it means fewer new field agronomists to add to the staff at universities and in industry. At one point a year ago, I was talking to a friend at Monsanto, and he said they were looking for 300 field agronomists. And it was very difficult to figure out where those were going to come from, because we'd add up all the ones being trained in the universities. At that point, there weren't enough to fill those positions, and that's just one company. Similar trends are happening in other applied ag disciplines and animal science and ag engineering and so forth. Can we reverse that trend before it's too late? That's a big question we're trying to answer. Defining the needs, we need research we need to meet those immediate needs, really present some research and business opportunities. And we need to further improvements in compatibility among hardware and software. We need to make sure that the hardware on a green combine matches up with the hardware that's on a red corn planter, for example. And those kinds of things we're working on, but there's still a ways to go before we can can move data from one implement to another and say that they're fully integrated and compatible. Steps that we need to take now are to define and develop those agronomic relationships and to take that systems approach to implement precision technology. Another part is data management. That's one we don't think about a lot, but whether we're working at a local level or a global level, we can use remote data collection and electronic systems. Multi-sensors and multi-locations, all part of the system for modern agriculture. And then instantaneous transfer of the information to an office somewhere, or it might be stored locally and picked up once a week or at some other interval. It might be processed at a central processor, or in some cases it might be processed immediately on the implement in the field that's collecting the data. GreenSeeker, for example, is collecting information about the chlorophyll status of a corn plant, processes that information, runs it through some algorithms and models, and generates the fertilizer nitrogen recommendation so that we can apply on the boom on the back end of the machine. All this happening instantaneously. And we're using multi-video. Not only the data, but photos and video and sound are all part of the system that we might be employing in the future to work with this. And it's multi-layer, current data and archive data combined, or both, all working together. We can utilize all those layers of information, both historic and live collected data. It needs to be georeferenced, and we can georeference now at centimeter accuracy and tell you exactly where that was taken. And the instant analysis is possible in many cases. And then along with that, instant decision support, action, and a response to that action. So let's take another poll here, see if everybody's awake. How many of you are currently using precision farming or working with clients who use it? The poll is open. See, there's 4 different potential responses there. Okay, it looks like about half, or exactly half, are using it yourself. 71% are working with clients that use it. 7% only that are not using it, and so that's we got a group of current and potential users, it looks like here. So that's good. Just to kind of go through an example of how this might apply in the fertilizer area, obviously my background in the last 40 years or so has been working primarily in nutrient management, so I tend to lean in that direction. We have what we call the 4R system for best management practices. Putting the R means right, the right source, the right rate, the right time, the right place. And then we look at it from an environmental standpoint, an economic standpoint, and also the social impact of our decisions. Along with that, we have performance indicators for those various 4Rs, and things like biodiversity, nutrient losses, water quality impacts, yield, obviously an economic side, return on investment. And from a social side, its impact on farm income, working conditions, soil productivity, and what we call ecosystem services. Things like, is the water supply from this agricultural area being deteriorated so that we don't want to drive our boats or we can't fish in the streams and that type of thing. If you want to dig into this and look at more information about the 4 R's, there's a website, www.ipni.net. It's the International Plant Nutrition Institute has a website with a lot more detailed information about the 4 R's. I'm going to just talk about them very briefly here. The right source means that we're trying to get all of the essential nutrients to meet the daily plant needs all season long. We can't afford to have that plant starving for any nutrient at any day during the season, or we're going to reduce yield. Tools that we use for that are regular scouting, plant analysis, simulation modeling is coming into play, new ways of placing fertilizer to make sure that it's easily available to the crop, and we have controlled release fertilizers that allow us to spread the availability out over the growing season. The right rate, we want to make sure we put the soil nutrient supply and plant demand in balance. So using soil testing and various applicator systems as tools. Remote sensing comes into play here, as well as yield monitoring and GIS mapping to make sure that we know what the variability in the field is and we can manage that if at all possible. Also, there's data integration and modeling with models such as Hybrid Bayes or Maize-N, which are 2 programs that University of Nebraska has released. You can get these programs for about $30 a piece and use your own data and your own information about your farm to predict what the potential yield is under different conditions. And GIS analysis can work either from grid or soil sampling or zone sampling of soils or other crop parameters, and field level budgets for nutrients and GIS analysis of all this information. And then following it up with variable rate application. The right time means that we want to assess the dynamics of crop uptake, soil supply, and the logistics of getting the nutrients to the field. Making sure those are all fit together so that, again, the crop doesn't run out of nutrients at any time during the growing season. Some of these same tools that we've seen before, soil and plant analysis, sensors, weather monitoring and simulation models, and integrating remote sensing with GIS analysis is opening some new doors in that area too. The right place, looking at the dynamics of interaction between the roots and the soil. That's what really comes into play as far as making sure the nutrients are where the roots are, and so they can be taken up as needed. So again, we get into managing spatial variability to make sure that happens, making sure we understand the crop needs, and that we limit any potential losses of nutrients so that we're keeping them in the field to be available to the crop. Some of the same tools that we've seen before can work to play. Well, a new one that comes in here is digital soil survey, because different soils have characteristics that are very important in nutrient movement as well as root growth. And all of these things interact. Right source, right rate, time, and place are interdependent. Sometimes the right time depends on what source you're using. The right place may depend on the source and so forth. So they don't act independently, but they're interdependent in making management decisions. Deciding when to put that product on. And here's an example of precision farming where we recreated the map out on the field. Don't usually see this with most of the nutrients we apply, but in this case we're using liquid lime. It's a very opaque and highly reflective material. We put on at a fairly high rate so that the areas that showed we had a high pH and didn't need lime, there's none applied. Areas that had a low pH, then there's a more intense white color in those areas. not perfect, but it kind of recreates the map and kind of shows us that variability and variable application is working. I'm going to over to Ed now for some demonstrations of some of the tools that are available that you might be interested in working with.
Yes. Well, thank you. And I'm going to change the screen